All right. So I would like to continue, analyzing the rolling of a disk, which we discussed yesterday, and because yesterday this is what we found. Actually, we found the acceleration of the center of mass of this disk. We found that it is 2/3 acceleration due to gravity multiplied by sine of that angle. Which means that it is less than if it were sliding on a. If we have a frictionless sliding block, we don't have this coefficient over here. Also, we were able to determine what kind of force, frictional force, is exerted by the ramp, and actually. This is not particularly important to find actually this frictional force, but in engineering, really, you will have to find out forces somewhere from a very similar solution. You will need to use this solution. I picked this problem because it is a relatively simple problem. In engineering problems, you will have more complicated, and if I still have a time today, we will try to solve another problem in which, let's say, I will let this rod to swing, and figure out how we have to design really this place. What kind of forces that axle allowing to the rod to swing has to exert. The situation is completely different, but the analysis is very similar to this one. It's just a little bit more complicated actually than this one. All right. So yesterday when we did that, we actually did everything using Newton's second law, several versions of it, right? Let me recall which versions. So we considered torque about the instantaneous axis and related it to angular acceleration. We considered torque about the center of mass and related it to angular acceleration. And we also considered translational motion, so motion of the center of mass, and related it to the net force exerted on the object. We used three versions of Newton's second law to find. It was not. If we had a particular problem, we didn't have to use all three versions. Now I would like to use Workenergy theorem to analyze this problem and see that the result will be similar, identical, really. How about if we now set a problem in such a way that we, what is the speed of this ball after of this object after certain amount of time after it is released? It is a relatively simple problem because then initial speed is 0. I could use the results which I found already from Newton's second law. So I can really find that speed using Newton's second law as well, because now I found already acceleration. So what will be the speed after time t? Now I see that center of mass moves with this acceleration. I found acceleration, right? So can I find where the object is going to be and what speed it is going to have at any instant? Yes, I can do that. And these are relatively simple calculations. So let's say speed of center of mass. Motion is just along this axis. I think I assigned axis x to this direction. Other two components are 0, so speed will be really equal to the x component of velocity. Now, x component of velocity, if I have x component of acceleration, is easy to find because what kind of motion it is. How acceleration depends on time? it doesn't. Right? So it's a motion with constant acceleration. In a motion with constant acceleration, integration of acceleration is simple. You will get a linear function. So, so therefore, speed of the center of mass at instant t, which is going to be equal x component of velocity in this situation, and therefore it is going to acceleration of center of mass, which is really x component of acceleration. This is magnitude of acceleration of center of mass. So acceleration of center of mass multiplied by t. And if I plug in now these, I will have that it is 2/3 g sine theta times t. All of this is constant. Now, where the disk is going to be at that time, at instant t? Well, it's a motion with constant acceleration, so integration of velocity is also simple. It will lead to what type of a function? Quadratic function. It will be quadratic function of time. So position, which will be really the x component of position of the center of mass at instant t, is going to be, well, and after integration, we will get that this is 1/2 times x component of acceleration of the center of mass times square of time. Well, which means that it will be 1/3 g sine theta times t squared. Again, this is a constant. Well, so let's find out now how the work energy theorem works in this case. So why don't we now see if indeed what we got is consistent with the work energy theorem for translational motion. So which kinetic energy I should consider then for translational motion? Which kinetic energy describes translational motion? It's not called about the center of mass. This is not called kinetic energy about the center of mass. It is called? Nope, no. And actually, it's good to not to confuse it. All right, so I will tell you various names of kinetic energies, and you pick it up. All right. So, is it kinetic energy of a particle? Is it kinetic energy of a total kinetic energy of a system of particles? Translational kinetic energy of the system of particles, or rotational kinetic energy of a rigid body? One of those four is the right answer. The one which describes translational motion of an object. Which kinetic energy? Why don't you consult with your neighbor and recall those four energies? Repeat the four energies which I just mentioned. Four kinetic energies. Talk to each other quickly. Why don't we repeat the four kinetic energy which I mentioned? Can somebody do that? Can you help me? Just say just one. Let's start with this kinetic. How about if you say one of the kinetic energies which I listed?
The kinetic energy of a particle.
The kinetic energy of the particle. This was the first one. Somebody can recall another one. Mark? No, translational kinetic energy was not. It's too trivial for a particle. It was translational kinetic energy of of an object. I really used phrase of a system of particles, right? Can you say another one?
Was there a translational?
He already covered translational.
What was the one with the rigid body?
Yeah, what was the one with the rigid body? Yeah, say it.
Rotational kinetic energy of a rigid
body. Rotational kinetic energy of a rigid body. Well, I will give you the most difficult. What was the fourth one?
Kinetic energy of a system of particles.
Be more specific. Which one?
Total.
Correct. The total kinetic energy of the system. So which one describes translational motion? Translational kinetic energy. Correct. Translational kinetic energy. All right. So I will concentrate now on the translational motion and use translational kinetic energy for that. And indeed, now do we recall what is the definition of translational kinetic energy? What do we understand by translational kinetic energy? We have to know the stuff, really. Yes, why don't you shout it?
Is big M the total mass?
Correct, yeah, so say it.
1/2 the total mass times the velocity of the center of mass squared.
Okay, correct. More precisely, actually, in the formula it was speed. However, I accept also square of velocity, because square of velocity is always equal to square of speed. And in general, always square of a vector is equal to square of its magnitude. However, there is a big difference in multiplication, right? Because square of velocity uses what multiplication, and square of speed uses what multiplication? Consult with your neighbor. All right, so for square of speed we have
number times a number.
Number times number, so it's product of numbers, and square of velocity is?
Scalar product.
It's a scalar product of two vectors, correct. Good. All right, so let's just check by how much did kinetic energy change after time t. After, so we release it, and after time t, what is the kinetic energy? So kinetic energy at instant t. It is at the same time equal to the change in kinetic energy. And why can I write that kinetic energy is equal to the change in kinetic energy? This is, again, a same situation as with balance on your checking account. So think about the change in balance on your checking account from yesterday to today is equal to today's balance. When does it happen? If we had balance 0 yesterday. Now, we release it from rest, which means that initial kinetic energy was 0. So in principle, I have k of t minus 0 equals change in kinetic energy. And well, let's find it out from the speed of center of mass, right? Because this is what the definition of kinetic energy. So it will be 1/2 mass of the object times 2/3 acceleration due to gravity, sine of the incline times t, and I have to square it. So the result is going to be 2/9 mass of the disk, square of acceleration due to gravity, square of the sine of the incline, and square of time. This is what would be the kinetic energy at instant t. And let's see which work actually is going to be equal to that change in kinetic energy. So what work would we have to calculate? Now consult with each other, because that way you will. I hope you will learn better than listening to what I say. Consult with your neighbor. Which work I mean, flip your pages right away to find the appropriate version of work energy theorem. I don't mind it. Do you have it? Did you get it? Because I mean, I know that on computers it's faster to find things. Well, no, I thought that you look at the notes. Have you found it? Who found the appropriate version of work energy theorem? Oh, maybe somebody remembers it. What say? Okay, you got it.
So change in kinetic
Change in translational kinetic energy
is equal to the work done on the center of mass.
The work done on the center of mass, more precisely net work done on the center of mass. So we have now to calculate work associated with all interactions. All right. So let's find out what is working. What does it mean, work done on the center of mass? It doesn't mean that the force is applied to the center of mass, because there is no force applied. There is no force ever applied to the center of mass. Center of mass is an abstract point, and we cannot exert a force on a center of mass. This correct. This is how we calculate the displacement. So we have to follow the displacement and see and take it in the calculation of work. It happens that all forces are constant as it rolls. Therefore, it's easy to calculate that work, because integration of the force will require, well, will allow us, when we integrate, we can take out force in front of the integral, and the work will be simply equal to force times displacement. Right? Okay, so let's see what performed work. Did the normal force perform work which increased, which affected translational kinetic energy? In other words, did normal force perform? I mean, was there work associated with the normal force? Who votes yes? Who votes no? Those of you who said no, you were right, and the reason for it was that why normal, why there is no, because the angle is 90 degrees. Displacement is in this direction, force is in that direction, right? So when we multiply by cosine of 90 degrees, yeah, so we have take the magnitude of the force times magnitude of the displacement times cosine of 90 degrees. This is 0. Who used that argument of those of you who came to the conclusion that the work was 0? That's good. All right. How about work due to frictional interaction? Who believes that, that there is work associated, a non-zero work associated with that interaction? Who believes that there is no work done associated with this interaction? You are right. There is work done associated with the frictional force. Now, who believes that this is a positive number, that work is positive? Who believes that it's 0? Oh, no. Who believes that it's negative? Very good. It's negative, right? Because displacement of center of mass is down the ramp, and frictional force is up that ramp. Okay, so how about if we calculate that? So work is equal, now we had that magnitude of frictional force was this, so it is 1/3 mass times acceleration due to gravity times sine of the incline of that ramp. So this is force, and the displacement, well, after time t, the particle moves to that location. Right? It started from from a point where we assign 0. So this is really the displacement. So I can multiply this by 1/3 g sine theta times t square. And now cosine of the angle is minus 1. So this is work associated with friction. Anything, how about now gravity? Does gravity perform work? Yes, gravity also performs work. Who believes that it's positive work? Who believes that it's negative work? It's positive because, well, the angle between the displacement and the force is less than 90 degrees. So when I calculate that work, I have just to take this component of the gravitational force along x direction because the displacement is in x direction. So I will have also mg, and consistently with this angle over here. Now I have to take, in principle, cosine of the angle between the displacement. I should take cosine of that angle. Well, however, this angle is equal to this angle here. You can see it. Think what will happen if I decrease this angle close to 0. Yeah, when this one gets close to 0, that the axis perpendicular to the platform is also is becoming more and more vertical. So angle theta is also here. So cosine of this angle happens to be equal to sine of that angle. So I can write down sine of that angle and the displacement. Times t squared. So if I recalculate that, I got a number that it is 2/9 of mass of that block, of that disk, times square of the acceleration due to gravity, times square of the sine of the incline, times square of the speed. This was the work done on the center of mass. Are we happy with that result? Who is happy with this result? Why? Why are you happy with this result? Because it is equal to the change in kinetic energy. Look over here. This number and this number are equal. Well, how about if we think about total kinetic energy after time t? All right, let's start again with this, how we calculate total kinetic energy. And we have now two ways of doing it, recognizing that it's a rigid body. I can think about, well, when the disk rotates and center of mass moves with this speed, well, I can recognize that the motion is a superposition of a translational motion and rotational motion about the center of mass. Or I can think about an instantaneous axis, and then this point doesn't move. So it looks like a rotational motion about that instantaneous axis. Why don't we calculate the total kinetic energy both ways? So which way would you like to start? Jessica, which way would you like to start? Consider total kinetic energy as a sum of kinetic and rotational motion, or consider total kinetic energy as just rotational kinetic energy, although it's a different rotational kinetic energy. Actually, I want you to discuss it with each other for a moment, yeah, because I'm saying that total kinetic energy sometimes is equal to kinetic energy plus translational kinetic energy, and I say that sometimes total kinetic energy is equal to rotational kinetic energy. And I know that you just see blah, 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 blah. So I want you now to discuss what is the difference between the two rotational kinetic energy. Consult this with your neighbor. How come that sometimes I can say that total kinetic energy is just rotational kinetic energy, and sometimes I say that it is sum of kinetic and rotational, translational and rotational kinetic energy for the same object. And maybe somebody can explain it to everybody. Talk to each other. Have you figured it out? Yeah? Okay. Why don't you have a try?
Rotational kinetic energy, it's about the axis.
Very good. If I say that total kinetic energy is equal to rotational kinetic energy, because with rotational kinetic energy, I always have to specify about which axis, right? So if I take it about the instantaneous axis, then total is equal to rotational kinetic energy, all right? And the other rotational kinetic energy was about the axis passing through the center of the disk, correct. So which one would you like to calculate first? I mean, I would calculate it. You just tell me which one. Okay, so let's calculate total kinetic energy about when we consider rotational kinetic energy about the center of the disk. So let's start with that rotational kinetic energy. So I have to take 1/2. Now, moment of inertia of the disk about the about that axis. So it is about axis passing through the center of mass. Moment of inertia of the disk about that axis is 1/2 mass of the disk times square of the speed of the radius. Now I have to multiply it by square of angular velocity, and since I don't have it, I will relate it right away to square of speed. So square of angular velocity will be square of speed. Oh, well, how about speed divided by radius of the disk gives me magnitude of angular velocity. So if I square it, I have the speed, magnitude of angular velocity. I mean square of angular velocity. So this is kinetic energy of the disk, and if I explicitly now, where is that? All right, so let's take a look what cancels. Here I have r square, and here I have r square. So r and r cancels. Now here I have 1/2 and 1/2. So I will actually I will leave this 1/2. How about if I write then? So it is 1/2 times 1/2 mass, and we have speed over there. 2/3 g sine theta times t, and we have to square that. So Well, if I square this 2, it cancels with those 2's. Do you see that? So 2, 2, and 2 cancels, and I will have just oh, how come that oh yeah, okay, so I have 1/3. I will have this mass, square of acceleration due to gravity, square of the sine of the incline, and square of time. All right, so this would be kinetic energy about the rotational kinetic about the center of mass. Now what will be translational kinetic energy of this object? Actually, we have already found it. Right, it is this one. So total is going to be equal to 2/9 plus 1/3 of mass of the object times square of the acceleration due to gravity times sine square of the incline times square of the time. All right, so this way we found total kinetic energy if we considered translational motion and motion as a superposition of translational motion and rotational motion. How about if we find out total kinetic energy now the other way? What is the other way? Consider motion as a rotational motion about the axis of rotation. Good. So it is 1/2 again times moment of inertia. Which moment of inertia? About the axis of rotation. Now, so it is about the instantaneous axis. So this time I have to consider moment of inertia about this axis. A moment ago we considered moment of inertia about this axis. I don't remember the formula for the moment of inertia of a disk about that instantaneous axis. Can somebody help me? And actually, I don't want you won't find it. Let's use the parallel axis theorem. Correct. So moment of inertia about this instantaneous axis is equal to the moment of inertia about the axis passing through the center of mass, for which I remember the formula, plus mass of the entire object multiplied by the distance between the axes. How far are the axes? By distance r, the radius of that circle, correct? And now I have to multiply it again by square of angular velocity, which is related to the motion of the center of mass. I see again that r square and r square and r square cancels here. So I have 1/2 times 1/2 times mass times this expression. Oops. No, it's not 1/2. It's 3/2 now. 1/2 is 1/2 m and m, so it is 3/2. Oh. But I think I made a mistake somewhere. Anybody found it? Now I have 2/3 g sine theta times t squared. Oh, no, I didn't. No, everything is fine, what I'm saying. Okay. So now 1/2 and 1/2 and 2 square cancels. Do you see that? Now here I have 1/3 square, and here I have 3. So I will be with 1/3 mass times acceleration due to gravity squared times sine of the incline squared times square of the time. All right. It makes me happy. Are you happy? Why? Because it matches the other total kinetic energy. So you see that no matter how we calculate that total kinetic energy, it works. All right. Now, that change in kinetic energy, because now initial total kinetic energy was 0 at the time of the release, right? So really, this is at the same time change of kinetic energy from the time to release to time t. So it is supposed to be equal to certain work. Now find appropriate work energy theorem so that we properly use it now. You can flip the pages. And where's the microphone? Oh, right there. Have you found it? Anybody found appropriate version of work energy theorem, which will allow now us to see if it is really equal to the change in the total kinetic energy? Now, I hope that you do not confuse it after tomorrow, which work and which kinetic energy to relate. This is going to be a subject. I mean, this problem is not going to be a problem because it's too time consuming, but an aspect could be there or something similar. So which work do we have to consider when we relate it to the change in the total kinetic energy? Total work done on the system, meaning then we have to calculate that work in what way? What displacements do we have to take? Well, how can you multiply a force by all of my displacements? Yeah, because my right hand moved differently than left hand. So what do you mean by all of them? It isn't by all of them. Not center of mass now. Center of mass will be useful only for one work. Not translational, gravitational, but it's coincidence. In a uniform gravitational field where the gravity is uniformly distributed over the object, so then gravitational work done on all particles separately is equal to the work done on the center of mass of the resultant gravitational force. But it's only true in a uniform gravitational field. Well, we have to consider now displacements of the particles on which the forces were applied. And we have to include both internal work and external work. Internal work is associated always with the shape of the object. So how much internal work is done on this disk? None. It doesn't change the shape. So that work is 0. Well, however, now let's find out how much work is done due to normal force. Yeah, how much work is done due to normal force, which affects total kinetic energy. So we have to take displacement of particles of the disks on which the normal force is applied. JD says that work is 0. Who agrees with him? Who doesn't agree with him? You should agree with him. Now, why? Where the normal oh, actually, JD, why don't you? Can you actually justify your statement that the work is going to be 0. Why do you think that it is going to be 0?
At the base of the disk, which isn't moving at the time that we're doing that.
Correct. When the force is exerted, the point of contact doesn't move. Now, when the point of contact does move, because, well, instantaneously, the point of contact touches the surface, right? And then the normal force is applied. Now, eventually it starts to move upward, right? As the wheel moves further here, this point moves upward. Well, so what about the displacement? That displacement, when it moves from that point to that point. Normal force is not exerted anymore, right? Think about it, how much, I mean, look at my foot now. Look at my foot. Yeah, so I'm lifting it. How much work did the floor perform? Well, when I'm touching the floor, the normal force is exerted. But as soon as I'm lifting it, I mean, in order to lift, first I'm pulling now that leg. When I'm pulling this leg, well, I'm decreasing that normal force, and actually when I lift it, the normal force is not applied anymore. Do you understand that? So the normal force performs 0 work. All right, why don't we calculate that work? So we have 0 work associated with the normal force. How about frictional force? How much frictional force is done on the disk? 0. And can you give a justification?
For the same reason of normal force.
Oh, well,
Because as soon as it
yes, I buy that. For the same reason as normal force. When the point is at contact, this is when the friction force is exerted. There's no displacement of that point. Now, when that point starts to move, frictional force disappears. All right. How about gravitational work? Now, calculating gravitational work from definition is complicated, because now we would have to calculate work gravitational forces exerted on all particles. Now, there was a coincidence, actually, but if you go set a number of slides back, when we actually calculated the total gravitational work, it turns out that it is equal just displacement of the center of mass. It's associated with the displacement of the center of mass. So indeed, I can still calculate that total work by taking gravitational force, so it is mass times acceleration due to gravity, times the displacement, and well, we found the displacement over there, 1/3 g sine theta times t square, and correct. Because now we have to take a cosine of the angle between the force and the displacement. Yeah, thank you. So we have to take cosine of this angle, and cosine of this angle happens to be equal to sine of that angle. So I need also sine of the incline. So the result will be 1/3 mass. I have this mass here. I have g and g, so I will have g squared. I have sine theta, so I have sine square theta times t squared. What have I calculated here? No. Total work. I calculated here the work due to all interactions. More precisely, it's network. I calculated here network. It happens that it is only gravitational equal to gravitational because the other two interactions do not result in work. And should I be happy with that? Why? Because it is the same as the change in the total kinetic energy, right? Remember that this total kinetic energy is at the same time equal to the change in total kinetic energy because the object was released from rest. Well, so I think that this will be the right point to finish the lecture. Now make sure, analyze again, I mean, watch the video and analyze again what work is associated to what kinetic energy. Yes, so that on the test on Thursday, you don't confuse kinetic energy. See, and remember also to include, when you think, always describe properly the nouns. Use those adjectives. Because saying now energy makes no sense. Saying even kinetic energy makes no sense. Before you came to the class, you always thought about kinetic energy. This is 1/2 mv squared. However, you thought only about what? A particle. Before you came to the class, you never thought about an object that it is an object. You always thought that it's a particle. It was approximation. Now, actually, we know why it is that approximation, because if I think about the object, what is that kinetic energy? 1/2 m, capital M, v squared. So it is not, 1/2 total mass times square of speed of that object. But now, indeed, it is not speed of the object, but it is speed of the center of mass of the object. So that kinetic energy is what? What do we call this kinetic energy? Translational kinetic energy. Now, if you think about, if you take an object as a particle, what is its translational kinetic energy? How is it related? How translational kinetic energy of a particle is related to kinetic energy of a particle? They are the same because center of mass of the particle is at the particle. Correct. Okay, that's it for today. See you tomorrow.